Specifically, well, first of all, the old quiz. So, what is the simplest and most straightforward way of combating overfitting? Uh, you might remember we did not talk about this in yesterday's class, but it is talked about in the pre-watch video things, the the Carpathy videos.
Data augmentation, I believe.
Well, not exactly. So, data augmentation, if you're doing data augmentation, there are some issues that can arise with it. I don't know if it's, it's a good way of doing it, but it's not really the most straightforward way.
So would the most straightforward way just be adding more data, I guess?
Yep, that is probably the best answer there. The correct answer here is yeah, it's D. Add more data to the training set. Which, of course, the reason why it may be simple, but it's not always the best answer is because you can't always do that. It's sometimes very hard to get more data, especially at a large scale. But yeah, that is correct there. Who were the two people who answered that one too?
I know I answered.
Name, so I can put it in my notes thing.
Nicholas Rose.
Nick. Okay, cool. And then who else had one? All right, that's fine. So, first thing here. Anyone recognize these two people? These two fine folks? Nope. You sure you haven't seen them anywhere? Alright, well, that's good that you didn't, because they're not real. These are neural net generated faces. Which, pretty cool, pretty good stuff. The paper that came out with these is a little old at this point. When it was pretty new when we first started this class, but it's been 2 years. But it's a cool little thing they've got going here. We always talk about, though, with pictures like this, I'm wondering how many the neural net generated, because these were the ones that were in the paper. I'm wondering how many the neural net generated where, like, the ear was up here, or, like, there was only one eye, or, like, the mouth was upside down, It's not going to get all of them right in generations, so I'm wondering how many were actually like this, where it was super believable, and how many it weren't that way. So today we're going to be talking about mainly optimizations, talking about what we can do with changing activation functions or learning rates or encoding or any of that. We're also going to talk a little bit about types of neural networks. But before any of that, we're going to talk about neural networks as functions again. And we've been harping on about that forever now. But we're going to look at them in a slightly different way again, because it's good to look at them in all these different ways. You can see the structural way that we saw at first, where it was this graph thing with input nodes and output nodes and everything. And then we had the actual written out function where we would write down the dot product and all that. We can also see them as these shapes. So here I have some data. Over here we have these blue dots, and over here we have these red dots. And let's say we're trying to do a classification. We're trying to separate these two classes. Now, a neural network could do that pretty easily. We can draw this line here. This line is y equals negative x plus 4. And in neural network speak, that would basically just be one neuron with a -1 weight and a +4 bias. As you see, we multiply our x by our weight, in this case the multiplier. So x input times weight plus bias. So there's our very super simple neural net making a very super simple line, and we can classify these two data fields with just one neuron. But not all data can be handled in that way. In this case, we have some blue dots over here and some blue dots over here and all this red in the middle. And we can't actually separate these based just on one line. They're not linearly separable is the term. But we could if we had something like this. This is y equals 0.2x squared. Now that's helpful because we have this nice parabola that is splitting those up. But the problem is a neural network can't do this. Our normal neurons, what they do is they do x times weight plus bias, and that can't model x times x. It can't model x squared. So we can't actually form this perfect parabola with a neuron without doing some weird stuff with the activation function or something like that. With just a normal linear activated neuron, all we have to do here is we can only handle linearly separable things. However, could do something like this. In this case, we have two neurons. Y1 equals x minus 1, and y2 equals -2x minus 4. And this means that we have these two neurons here, and they can, combined with some other neuron probably controlling them on another layer, do this classification. So two neurons each separate this data linearly. One in the next layer determines which side is which. Basically, it's the controller in that case. And that works. That should work then with our just our linear functions. It's still technically, it's kind of a cheat because it's still only going to work on linear separable data. A neural network with no activation will not really work super well on any sort of non-linear function, but that's why we have activations, and we will talk more about that in a bit. But the important idea here, anyways, is that these neurons, like we can say that they're a data structure and a function and all that, they're also shapes. Usually high-dimensional shapes, many dimensional shapes. And they're shapes that are carving out a space usually implicitly, but, in this case, we have, here's the same data 3 times, and we're trying to do a classification. And we're seeing how different numbers of neurons can create, in the hidden layer specifically, can create a more dynamic shape that can capture these points a little better. So in this one, we only have 3 neurons, so we get this kind of blobby shape here. It's not great, but it's able to capture a bunch of the red ones. It's able to do a, better than average classification, better than random, let's say. But it even captures one of the green ones on accident. If you do 6 hidden, it's not much better, but it avoids that green one kind of, and it can reach out this like amoeboid looking grabber here to grab this one. And then with 20, you can go even further with it. Now, this particular graphic is kind of showing, I would probably say like this one over here, this 20 hidden neuron one is overfitting. But at the same time, I don't know that these two classes are super well defined anyways. But, good stuff though. So this basic idea with this is just neurons are shapes. It's just kind of an add-on. We won't be talking about it much more in the rest of this, but it's an important other way to look at these things. Any questions on that?
Yeah, you mentioned that you would say that the 20 hidden neuron is overfitting. How can
Mhm.
you tell if it's overfitting or not?
Great question. So the reason I say it's overfitting in this particular case is that this doesn't seem to really follow much of a distribution. Like, if you were to, in a human way, like take off all this red and this green and just have the dots, and you were to separate them and try to separate them into two groups here, I wouldn't come up with a shape like this. Um, Now, if remember, we're assuming at this case that these are training data points. These are points that are used for training, and then testing data points will be similar, but they're not going to be the same points. So, given that these dots are here, I don't know that we can extrapolate that we're going to find a bunch of red dots along this line right here, right? Like that seems a bit unlikely, but it might be true. It depends on what the actual testing set looks like. But the real strict definition, if you want to get down into the weeds about it, it's if you have your training set and your testing set, and your model runs better on your training set than on your testing set, then technically it's overfitting. Right there, that's enough to um, classify it as being an overfit model. Because at that point, it means that it is learning too much from the training set and not enough about the actual problem as a whole. It's not abstracting enough. Um, so yeah, that's. I know that's an overly complicated answer in some ways. In this case, we can't tell for sure because we don't have a testing set. We just have this training set. Um, but I'm only guessing that it's overfitting because it looks a little weird. It doesn't look like a pattern that would be natural in a way.
Max,
Yep.
yeah, okay. Have you talked about dropout as well
That's
for to
gonna
be used for overfitting?
that's later in this lecture actually.
Okay, that's fine. Okay,
Yeah,
great.
I think it is. I'll have to check, but we'll see. If not, we'll talk about it at the end. Um. So, anyways, ooh, this would be fun. I didn't want to go off on too many tangents here, but this is a really good tangent. So, this is a great site. Go to it in your free time, just for funsies. You get these four little data sets you can mess with, and you can try to get the neural network to fit these shapes by adding hidden layers or adding neurons in a hidden layer. And you can do all sorts of stuff. You could even have like special inputs. That's something we haven't talked about much, but we will be a little bit later today. You can be really creative with these inputs. Like you can go ahead and try taking one of your inputs and squaring it or something. See what happens. Um, we talked about how neurons can't do x squared inside of themselves internally, but they certainly can if you give them x squared. They can use that at that point. And this one's a really hard one to mess with. Let's see if I can. Not that many. That'll do. Let's see what that'll do. All right, it's converging, sort of. Yeah. So it's taking its time, but you see it's kind of coming to a solution, not a very good solution. But yeah. This is a really cool program though. You can change all sorts of stuff, learning rate, activation function. Anyone want me to try anything on here? All right, I think we'll get back to it then. But this is an awesome, fun little toy to mess with. Um, that's it for neurons with shapes, though. As shapes, though. Um, let's go on to hyperparameters. So, what's a hyperparameter? This is a parameter of our model. A parameter could just be like the weights are usually if people say what are the parameters of your model, these are going to be the weights and the biases. But a hyperparameter is specifically one of these like deciding factors of the model that we make up our mind about before we even start training. This is going to be something that either doesn't change or changes in a set way. It's not learned through backpropagation. It is going to help us determine the structure and the training process of the network. And we have a lot of examples of these right here. We have the learning rate as a hyperparameter. The loss function is itself kind of a hyperparameter. Mini batch size, we'll talk more about mini batches in a bit. Number of hidden layers or neurons, just the architecture of the network. How we initialize the weights, because we've just been saying, okay, we randomly initialize. Why do we do that? Is there a better way? All good questions. Even the activation functions we use. All of these little things that we can come up with prior to learning, these are going to define a lot about our network and tell us all sorts of things about how our network's going to function or how it will fail to function. So how do we, and this is an old slide, and I keep forgetting to update it. So I was tired when I wrote it, and I wrote metaparameters instead of hyperparameters. I don't know what metaparameters are. I think they're made up by my tired brain. But that was like 2 years ago, and I still haven't changed this slide. Hopefully I'll remember this time. Anyways, there are 4 kind of ways you can go about, or 4 general ways you can go about selecting hyperparameters. The most common probably, and the most simple, is just manually select based on the knowledge of the problem and change it based on testing, usually with something called a validation set. This is just, you're trying to get a feel for the problem. You might know certain things about similar problems or about problems that maybe you just know what the structure of the problem's kind of like, so you can kind of focus on that to figure out what it should be. But you can use that information to help you just kind of get a start and then refine it by testing it with various different parameter choices. You could also identify a whole range of possible good values, basically an extension of part 1, where you just decide this range and test each one on a validation set one at a time until you have a best one, and then you stick with that best one. You could do a random search where you're just guessing through all of them. And then the main, big one, I think there's been a few recent ones that are kind of big. I think MIT came out with one maybe a year ago that was kind of interesting, but I don't think it's taken off a huge amount yet. But the last one that's common is a Bayesian optimization approach. We aren't going to talk about it much, but there's a Wikipedia article if you want to give it a go. But you can see a lot of these common approaches are some degree of guess and check, and that's okay. It's not perfect, but it does the job. There's also some less common ones, and some of them can be very powerful. One I like a lot, mostly because I like the type of algorithm it uses, is these evolutionary algorithms or genetic algorithms. And with those, you can create something called a genetic neural net that basically it either learns hyperparameters using genetic algorithms. Again, we're not going to talk much about genetic algorithms here. I wish we could, but we're going to try to stay not too many tangents here. But it can use that to figure out hyperparameters, or sometimes even the actual parameters themselves. There's also certain gradient-based optimizers, so basically running your gradient descent sort of thing on number of neurons or something like that. Those exist and can be used, but they're not super common. And then there's something called tree-structured Parson estimators. This is a tree-based algorithm. Again, we're not going to talk about it much, but these are some options that are out there. For the scope of this course, does anyone know any German here? So this is a German word, Fingerspitzengefühl. I don't know German, but I know that word because it's a good word and it's good for like chess and stuff. I like chess. It translates to fingertip feel, and that is kind of the ability to operate with intuition and instinct, and to it's not a full instinctual thing. It's definitely got elements of um, built up knowledge, but it's the ability to act in this intuitive feeling sort of way. And in this course, rather than go into do a deep dive over like 3 different lectures into these different hyperparameter tuning techniques, we're mostly going to be trying to build up our Fingerspitzengefühl when it comes to these tuning these hyperparameters. We're going to mostly do trial and error type things. Sometimes I'll give you decent starts in the skeleton code. Sometimes I won't. I think one of them I gave just a placeholder number of like 10,000 epochs or something like that. Yeah, by the way, change that. You don't need to actually do 10,000 epochs in training unless you're doing a very specific kind of network. You know, you can change anything in the lab's skeleton code. Go right ahead. It's not a problem. But yeah, so when we do hyperparameter tuning, we're not going to be using any particularly sophisticated techniques. I would honestly just do some combination of these first 3. Will do the job. Mainly, this is kind of our motto one, though. And this is, we're going to try to get some degree of knowledge, build up that knowledge on the problem, and then change the parameters based on that, testing from that. Learning rate. We've messed with learning rate a bit before. Symbol eta here. This is going to be the multiplier for our delta value, and is going to, or technically our adjustment, and decides how fine-grained our learning is. We talked about it in some detail already, but the worthwhile relationship to know here is that a high eta, a high learning rate, is going to mean faster learning, but it's going to be less precise, and it might just not converge. It might do that thing where it kind of spirals off and just gets worse and worse because it can't fit almost into the valley of the function, if you want to think of it that way. And then a low eta, a low learning rate, this is going to converge much more slowly, but much more smoothly, and it will allow us to sometimes converge on problems that we wouldn't be able to otherwise. So usually we end up using a decaying learning rate. That's usually the best. In other words, you start with a really big one, 0.1 or 0.01. I know that doesn't seem big, but in learning rates it's huge. And then it decays and gets smaller and smaller until it comes down to being like 001, 301, 401, It can be pretty small. Though if you're not doing a decaying learning rate sort of thing, you usually want to start with one of these smaller ones. So that's important to know. Loss functions. So we've talked a little bit about them and what they do, and we've gone in deriving MSE and such. But let's go over a few other options we have. So we have MSE. We talked about that. That is going to be the average of the squared difference between the predictions and the actual observations. It's continuously differentiable, which is always nice. And the nice thing we have here is that because we have that squared term, it's an extra penalty for predictions that are very far off from what we expect. So the farther away it is, the more it's going to punish it. So outliers are heavily punished when using MSE. on the contrary, we have MAE, which mean absolute error. This time you're not squaring it, you're just using an absolute value function here. This does not punish outliers nearly as much, but it can be useful when, in fact, you don't want to do that, when you want it to be particularly outlier insensitive. And it's also not continuously differentiable. If you think about an absolute value function, it's kind of a V shape. So on this side, on the positive side, it's differentiable. On the negative side, it's differentiable. But at 0, it's just this point, and therefore it's not differentiable. Cross-entropy loss. So this is used mostly for probabilistic classification. Cross-entropy loss decreases as the predicted probability approaches the true value. So as the probability gets closer, it's going to refine it less and less. It's going to be a little more accepting of it. But because it's following this log function here, it's going to be very, very high when it's very far off. So that's the way to think about that. Is it punishes predictions that are both confident and wrong. So if it ends up selecting one class, but with a very, very low probability, it's just the best possible guess, then it's not going to punish it that much. But if it's like, all right, this is definitely class number 2 or whatever, I'm 98% sure of that, it's going to punish it very hard if it's not actually true. And a few other quick ones here. I'm not going to go over all of them. They're used in various things. All of them have at some point been used in neural nets. But there's all of these different ones out there. In fact, if you do autoencoders a lot, which one of the recent projects I've been doing has a lot of them, pretty much every paper that comes out with an autoencoder has a new, different loss function that they just throw in there. A lot of changing loss functions for autoencoders, but these are kind of a sampling of them. And with that, does anyone have any questions on loss functions? Alrighty.
Yeah.
Oh, yep. Sorry, go ahead.
Is there ever a situation where you would use multiple?
Yes. Well, actually, the research I'm working on has multiple just because it has one that's used for training and one that's used for a form of testing, or sort of. A little more complicated than that. But and the other thing you'll do when you're doing a testing thing is you'll actually define the loss function to be some combination of other loss functions. So either you might do that if there's multiple steps of the network in which you're checking things, or you might do that if there's multiple things you care about in the network to get right. And if I'm talking abstractly, that's because that's the only way to get around it in a super good way. But we'll actually have an example of that in this class. One of your projects is style transfer. And in that, we're actually using one of these compound loss functions. So yeah, sometimes you will use multiple loss functions, but it's usually for training, it's going to be one that is composed of many other smaller ones. And again, you can customize these. You can make all sorts of different variants and things like that.
Right. Okay. Thank you.
No problem. So, which to use kind of depends on what you're doing. If you're doing probabilistic classification, probably use cross entropy or binary cross entropy. Both of those are good. Standard cross entropy is really good for if you have many classes, obviously. MSE, not as great for this kind of probabilistic classification sort of task. It's a lot better for things like checking like generation of images, it can be pretty good with. It can be used for general classification problems. It's also quite good for regressions. If you're doing some sort of like neural network that's trying to model a regression, it's very good for that. But in the purview of this class, the main things you'll be using are probabilistic cross entropy, binary cross entropy, and MSE. Maybe you can try MAE at some point, but those are the main ones we'll be messing with. Weight initializations. This is fun. So, why... Shut up, phone. So why don't we initialize all the weights to 0? Why don't we just say that it's just gonna be a big 0 matrix? Well, if you do that, your neural network's basically going to act as a linear model. Why is my phone yelling at me? I'm going to turn it off in a second. Basically, what will end up happening is each layer will have the same weight adjustment for every single neuron, which is not good. That means you will just get the same change. All the neurons in a single layer will be the exact same value, and from that, your neural network will act as a big linear model. And that's not good because, as we saw earlier in this, neural networks can't do that without their useful activation functions and such to model these things. So we don't want 0 weights. We don't want all 0 weights. So what we usually do, and this is pretty much all the time we're going to be doing if we're making our own network. If we're using a library, it's going to use something a little more sophisticated, is we just have random values. This is much better. We don't have that problem where we're going to accidentally cripple our model. But we do have some problems. And these are kind of problems that are endemic to neural networks. They will continue to be part of neural networks forever. There are many papers that are introducing many algorithms just to combat these issues. And these are the vanishing gradient and the exploding gradient problem. Briefly, these problems are when in very large networks, specifically networks with many, many layers, the gradient may end up the backpropagation gradient that we've been using may decrease so much that as it goes backward in the network, that it basically vanishes. It gets so small that it can't change anything, or it gets so, it might even end up going past floating point's ability to model it effectively. And the other thing is exploding gradient. In some networks with very large feed forwards, this exact sort of same thing can happen the other way. We're not going to go into too much of why this happens at this point in the class, but it's worth knowing these exist, and just having random initializations will do that, or will exacerbate the problem. Yeah?
When you're selecting random weights, would it make sense to make sure that all of these weights are unique?
You don't need to.
Okay.
Yeah,
because
it won't.
I was wondering, because I was trying to imagine like you were describing how if you have all zeros earlier it would cause issues, and so I was wondering if you had, for example, a small set of neurons with similar or the same value or weight on them, whether that would result in just small linear things within the overall graph, if that makes sense.
Yeah, it's at that point, because it has all the other neurons in there that are randomized, it should actually still end up being able to change those in a more fine-grained sort of way.
Okay.
But yeah, it's the real problem is just when it's only zeros or only one value.
Mm-hmm.
Another solution, though, to this is, well, this is kind of a family of solutions at this point because there's been so many variants of this as well. But there's something called he et al. Initialization. It was the guy who came up with it, was his last name was he, and then he had a bunch of other people working on it. So he et al. Was the paper, and his initialization is still random, and you'll find that most of the things are still some degree of random, but the range is going to follow a normal distribution based on the size of the layer. So I'm not going to get, again, I know I'm glossing over a lot of things here. That is the scope of the course sort of thing, but the basic idea is doing this is going to make it a little more fortified against these issues that come from vanishing gradient. But yeah, that's all I'm going to say on that. But if you want to learn more about it, if you want to get more into the specifics of it, you can look at that as well as another one in this nice Medium article. Xavier is also used a lot. In fact, I think PyTorch uses Xavier under the hood or some variant of Xavier. But both of these are options, and they both do some sort of random with distribution on top. So hidden layers. Number of hidden layers we're going to be working with is can be something that's fun. We can both figure out how many hidden layers and how many neurons per hidden layer we have. Of course, usually we're going to have different numbers of neurons in each different layer. And yeah, that's kind of how that is. That's the basic idea. Generally, though, the more hidden layers in a network, the more complex a shape it can make. We're talking about the shapes that the neural networks can come up with, and the number of hidden layers you can have is going to increase that dramatically. It's going to be almost act like a multiplier as to how complex your shape can be. If the problem's linearly separable, i.e., you have two very distinct classes, you actually don't need any hidden layers. You can just have the output layer. You can just do it with one neuron, or however many neurons the output size needs to be. And the usual way we're going to look for this hyperparameter specifically is with cross-validation, which I don't think I've talked about too much. Cross-validation, the basic idea is we split our data set up into several chunks, and we'll use a number of these chunks for specifically our testing data set. And we use n-1 of these chunks for training, and then one of these chunks for validation, and then we switch which chunks we use. So we end up actually trying every single combination of those. And once we've done that, we can, once we've tried all of these different combinations, we can get a good view without spoiling our data set, is what we usually call it, of which of these different architectures is best. But when it comes to the hidden layers, again, the more hidden layers you have in the network, more complex shape. The other thing, too, I don't want to get on another crazy tangent, but this is, there was a paper that was out, I think, in either the 80s or 90s. It's a while ago. That was showing that if you have an infinite number of neurons, one layer can do any computational thing. Should be able to do any computational, compute any computational function. I think that might be limited because I don't think that a single one-layer network is actually Turing complete. So I think it's somewhat limited, but it's not that adding layers gives you more capability than you can get with a single layer. The thing is, if you have that single layer, you're going to need a lot more neurons. And it can get to the point where to do very simple functions, to model these very simple functions with one layer, you'd have to have more neurons than you could possibly fit onto any computer in the modern day. But just by adding a few layers, you can handle those problems a lot more quickly. So, activation functions. We discussed that before. Mostly just the job of these is to compress our outputs into some sort of shape that we like. So we have sigmoid, of course, between 0 and 1. It's always a good one. Differentiable the whole way, so that's helpful. Tan H, negative 1 and 1. Also differentiable the whole way, also helpful. ReLU, we have talked about that in a little bit of detail, but not too much. It's a simple one. It's not computationally difficult to do. Our computers can do it without a lot of energy. But that being said, it is super, super useful. It is probably, if you're doing internal layers, right? If you're doing your hidden layer activations and you're working with images, it's almost always going to be ReLU or a variant of ReLU. It just works very, very, very well. ELU, that's one of these variants. At this one, we have this nice little alpha value here. We can set that to be whatever we want it to be, but usually it's going to be something around, it's like a 0.5, 0.2, something like that. And it's going to kind of just staple this tail onto the function here. So that makes it differentiable the whole way through then. Good little thing. We have softmax. Softmax, it doesn't really fit this nice shape that I can show graphically, but this one is going to take in an input of n, and it's going to compress it into a vector of k size with range 0 through 1, such that all the sum of the whole vector of k is 1. In other words, it's going to put it in very much the same sort of structure as a one-hot encoding, except instead of actually being one-hot where it has 0, 0, 0, 0, 1, 0, 0, 0, it's going to have 1, 1 in there. It's going to have it probabilistically distributed. So you can tell where this would be useful. This is used when we have a neural network that's doing some sort of probabilistic work, usually probabilistic classification. So when we're trying to figure out, all right, what percent likelihood is this a dog versus a cat? You can put a softmax activation on at the end and get a degree of confidence in the neural network. The network can tell you how confident it is in any particular option. It's almost always used only on the output layer, though. You're almost never going to use this internally because it's not actually that helpful internally, and it takes some more computation than something like ReLU does. Whenever you see a classifier that's rating its guesses, like you might see where it has a few different guesses in the top 4 around the screen, that's using softmax probably. And of course, there's a whole bunch of other ones, variations on ones we've seen. There's a cosine. You can use cosine. That's kind of fun. I think the main thing that's used for is for things that are specifically following some form of cosine-like or sine-like wave. But yeah, we have all these different ones here. Any questions on these? Cool. So for image processing for our class, mostly ReLU, honestly. Mostly just ReLU on the internals, and softmax at the end. That's going to be a lot of what we do. That said, feel free to experiment. Try some things. It might give you some really good results. Just make sure that it lines up. as we saw with the homework, I had an extra question in there that was something along the lines of when are we going to get to the end? When is it going to actually reach that 1.2 value? That was, I think it was 1.2. That was our y value we were hoping for. And the answer to that is never. We will never get there because the last activation function was a sine function, and sine is between 0 and 1. So it will only ever output at most 0.999 something. Whatever the highest version of that is with floating points. Most accurate, most precise version of that. So yeah, feel free to experiment with all of these. It's neural networks. You can do a lot of experimentation and trying things, and you can find some interesting results. So, optimizations. How do we make our neural nets better? Well, when hot encoding, we talked about that already. This makes it easier for our neural network to understand these categorical inputs because it doesn't have pre-assigned relations of different categories. Also, fun fact, we talked about this a little bit already, if we use our softmax activation and we are representing the class with a one-hot style vector, so we have our class label, instead of being like a 7 for the 7th class, it would be a one-hot vector representing a 7. We can get our probability distribution with the number at index I being the probability of the record being that class, and then we can do a comparison really easily between the two. It allows us to work with this one-hot encoding a lot better when we have softmax. So for images, though, when working with images, we are still going to use it to represent these labels. Like, I think we probably do. I'm pretty sure we do that in Lab 1. But that being said, we don't do it for much else, because image data isn't like a category. It's going to be pixel data. So for images, mostly just values. Mostly going to be floating points between 0 and 1, which we'll scale the images to. Here it is. Gustavo was talking about this at the start. So earlier, we talked a little bit about overfitting. And overfitting is a tough issue because it basically means we're learning too much about the training set and not enough about the entire task itself. And of course, the symptom of this is we perform quite badly on the testing set while we did pretty well in the training set. You might be getting like a 90% or something, or 99% on the training set, and then you run it on the testing set, and you end up with like a 65%. Like, it's barely even classifying it close to correctly. So dropout is one of the ways we handle this. Obviously, the best way is to just have a bigger training set. Not always possible. Sometimes very expensive. Sometimes takes a lot of time. Dropout is one of these ways that we can do it in a more friendly way for us in a lot of ways. So what we're going to do with this is every training step, we're going to randomly remove some neurons with a fixed probability. So we're going to set some probability, a lot of times it's 0.1 or 0.2. And we are going to, with that probability, remove specific neurons just for that training step. When we do our forward pass, they don't fire, regardless. They're going to output 0 every time. And what that will do for us, why that's effective, is it will force other neurons to compensate during training. Because we're not using these specific dropped out neurons, other neurons will have to take their place. And that means that we're reducing the power of any individual neuron by making the rest of the network improve. And hopefully in doing that, it will lead to a more generalized solution to the problem instead of a very specific solution, which might almost be equivalent to memorizing the training set. So Dropout's really good. Dropout is used extensively all the time for everything. It's super, super helpful for avoiding overfitting, especially with neural nets, because the problem with overfitting is the better your model is, almost always the better it's going to be at overfitting. And neural nets are really good. They're I'm not saying they're better than all the other machine learning models. It depends on what you're doing. But they're quite good. They're quite they can learn these things quite effectively. And if they see a pattern, they're going to learn to mimic it. So it's important to make sure it's mimicking the big abstract patterns that we're looking for instead of just very specific little blips in the training data. Any question on Dropout? Cool. Oh yeah, so Keras. We will be using Keras in Lab 1. We will use it in the future. If you want to use Dropout in Keras, that's really easy. You could just add it as a layer with the dropout rate, and it will do all the dropout for you, which is super, super nice. Especially because then when you run predict, it's going to stop running this, because you don't want this running when you're testing. This is just for training. It's going to make it a lot worse if it's done during testing. Mini batches. So when we train our neural network, we often feed in more than one example of the training data at once. These are mini batches. The size of these can actually determine how quickly our network learns. And in fact, there's an interaction between batch size and learning rate. We talked earlier about decaying the learning rate as we go throughout the training, but you can actually sometimes increase the batch size instead. And there's a whole paper on this. I think it's called it's one of those papers that I don't really like the name of, but it's got really popular, and it was something like, don't decay learning rate, increase batch. I can't speak today. Don't decay learning rate, increase batch size, and that's just the title of the paper. And that's what they're saying to do. But yeah, if the batch size is very small, the neural network will take a long time to converge. But if it's too big, the model might end up being weaker. So, and it might end up actually slowing down as well if it's too big, depending on how your memory's working and your caching and all that. So the point here with mini batches, try a couple sizes, usually 32, 64. See how long it takes to train, and usually you'll end up with a pretty good one eventually. Yeah, batch size is good. Batch size. It's almost never good to just do one at a time unless your model is specifically made for that, or your task requires that. Reinforcement learning, it's sometimes done that way, where it's just has to be one at a time, but that's a story for another time.
Max, yep. This is Gustavo. I will have to go now. Thank you very much.
All right, see you, Gustavo.
Oh, bye.
Yeah, it looks like we are running a little low on time. Let's see, how many of these do we have left? Oh yeah, we got a lot still. Okay, I'll go fast. We'll use fast mode here. So yeah, mini batches, 64, 100, 128 are good starting places. You get trial and error to find them. And let's talk about some of the different types of neural nets. We have seen a few of them before. By the way, I'm taking all my diagrams from here because when I made these slides, I didn't want to have to make a new diagram for each of these, and this place had some nice ones, so go check out that article. But we've seen these before. We have our inputs as these yellow nodes, green nodes are hidden, orange nodes are output. So we can have no hidden layers, that's a simple perceptron, one neuron. Feed forward, several perceptrons put together with our hidden layer. Or we can have a deep feed forward, a deep neural network. That's going to have multiple layers in the middle. By the way, that's what deep learning is, basically. It's just it's just deep neural nets. It's a fancy term, but it's not really meaning much. Recurrent neural nets. These are great. These are good for sequence data, such as text or video, things like that. Recurrent neural networks give the last output of the hidden layer back to itself as an input. So here's kind of a look at that. There's lots of subtypes of these too, like LSTMs and GRUs. It gives the RNN basically a small amount of memory. And another way to look at this is, here's an unfolded one. So you have your input, your neuron, and then an output. And what this will do is you can unfold it to see where you have input 1, input 2, input 3, and it's all going into the same neuron, but one of the inputs to this neuron is the previous output. LSTMs are similar. I think we'll be having a lecture on them later in the year. Inside these neurons are special gates, basically. These are learned gates with their own activation functions, and they'll determine what the LSTM actually remembers and how far back it remembers. Hopfield networks. We aren't going to mess with these too much, but they're special networks that are fully connected to each other. Every neuron during training acts as, or before training acts as an input, during training is a hidden, and at the end is an output. So what these are basically do is they learn to mimic input-output patterns in an exact way. They're pretty useful actually for image recognition tasks, but we're not going to talk about them too much because there are better versions these days mostly. Boltzmann machines, these are very much like Hopfield networks, except that some of the neurons are actually hidden. We're actually going to have some of these where they're not inputs at certain points. We'll just have sub-inputs, and then it's still going to follow this Hopfield network sort of situation, though. And it gives it a little bit of extra computational units, basically. It's a better version in a lot of ways. But there's hundreds of variants, thousands. You can cobble these things together in any sort of architecture you want using special neurons or special activation functions. You could do all sorts of crazy things. Very special layers even. There's so many different neural networks, and we aren't going to even scratch the surface, really. It's a whole area unto itself. But we haven't talked about the big one, the one that is going to be the most important one in this class for sure. And that is the convolutional neural network. Here's our links, and we will be talking about that next week.